Welcome to video 21 on the TTB course. This video is from part 5 of the course. In part 5 we introduce a set of TT platforms. We then illustrate how these platforms can be applied in a range of case studies. In this video we introduce the platforms. The material in this video is based on ERES 2, Appendix 2 and Appendix 3. If you haven't read these parts of the ERES 2 book, I suggest you stop the video now, read the appendices, come back and watch the video again. The material will make much more sense if you've had a chance to read the book first. So let's begin with an overview. We're presenting a range of platforms in this video and in the associated book that are intended to bring together the material that we've discussed in previous videos on this course and to provide you with a means of developing TT systems quickly and reliably. So we're aiming to provide a range of different platforms that can be implemented quickly and easily, allowing you to prototype a reliable TT design with reduced effort. The platforms that we present are designed to cover a range of different safety integrity levels. So if we start by viewing these from the perspective of IEC 61508, the generic international safety standard, we'll be looking at a range of platforms in this video that cover systems from SIL 0, which are not safety related, up to SIL 3, which are a high level of safety related system. This is not the highest level that we get to in IEC 61508, but it's the highest level that's commonly used in the majority of systems. The equivalent safety integrity levels or ASIL levels in standards such as ISO 26262 are also shown in this table. So we're talking about designs that range from QM level up to ASIL D level according to this standard. Other standards are similar. So we're running up to level B in DO 178. This applies to passenger aircraft. Up to class C for medical designs. PLE designs according to ISO 13849. Household designs up to class C. To reach these levels, and the comparisons between the different standards are approximate. It's never possible to say precisely that any particular standard, a level in any particular standard is exactly the same as a level in another standard. But what we're saying here is that these are roughly equivalent levels in the different standards, and particularly what we're saying is that these TT platforms, the bottom part of this table, can allow you to achieve the different safety integrity levels that are shown for the various standards in the columns above. So we start, for example, with a correlator A0 design, and we work up to, for example, a duplicator A22 design. You'll find in the ERES 2 book in Appendix 3 a table that lays out clearly exactly what each of these labels means and lays out what A and 1 and A11, A22, etc. means. It will be worth taking a look at that table at the beginning of Appendix 3 in order to familiarize yourself with what the naming convention for these platforms means. We're going to look at some of these platforms during the course of this video to give you an idea of what's possible using this type of approach. So let's start with what we call the foundation platforms. These are presented in Appendix 2 of the ERES 2 book. We don't recommend that these foundation platforms are used in safety-related systems, but they can still be useful. So let's begin with platform TT00. This is a simple superloop platform. So this is the complete code framework that we might use. For example, for a central heating system in a house. So we have an initialization function, and then we have a super loop. So there's no timer ISR, there are no interrupts at all in this design. We simply call these three functions in sequence repeatedly while the system executes. So we have a very simple process for releasing these three tasks: get required temperature, get actual temperature, control the boiler, and we simply release these tasks in sequence while the system executes. If we'd balanced these tasks using techniques we've discussed earlier in this course, we would have a reasonably high level of control of the system timing, but this kind of design is very brittle. If we change the behavior of one of the tasks, that's going to have an impact on all of the other tasks in the system. We don't recommend that you use this for anything other than very simple designs, but for such very simple designs, it's not a bad platform. The next platform that we consider is worth identifying is TT01. We use this as an introductory training platform. It's a platform, it's called in the Embedded C book the SEOS architecture, Simple Embedded Operating System. We use it for teaching purposes. We don't recommend that you use it for practical designs, but it's useful as a teaching platform. What we do here in this architecture is we have a main loop that's fairly similar. All we do within the super loop in this case is put the processor to sleep. We then have a timer ISR, and we perform all the activities for the system from this timer ISR. So any functions we want to call, for example, any tasks we want to release, they're called from this update function here, which is the timer ISR. So our system activity is a sequence of calls to this update function. There are many designs on the planet today that operate using an architecture that's similar to this, but at this point I would recommend that you consider this only as a teaching platform and don't attempt to implement practical systems using this approach. TT02 is a platform that's described in detail in the PTTS book that you may already have looked at earlier in this course. This is a typical code framework that we would use with this platform. We'd set up our scheduler, we'd call the initialization functions for our task modules, we'd add our tasks to the schedule, and we'd start the schedule. This kind of design is typically used for single mode systems. Not always, but it's usually used for single mode systems. It has a simple TT scheduler and very limited runtime monitoring. For example, there's no monitor, no predictor, no warrantor components typically in this kind of design. This kind of architecture and the code from this book have been used in designs that are in use across the planet at the present point in time. Overall, I still wouldn't recommend that you use this approach for safety-related systems, but it does provide a useful foundation for reliable systems. It's been used in space systems, deep sea monitoring, etc., where there are no direct safety implications, but where reliability is an important consideration. If your system is safety-related, or you have high reliability concerns, I suggest you consider one of the recommended platforms for use in your system rather than one of the foundation platforms that we've just looked at. In the remainder of this video, I'm going to focus on the recommended platforms for safety-related, high reliability TT systems. So let's start with the correlator platforms. We've looked briefly at these in several of the previous videos, and I'm going to look at the internal operation of these platforms in a bit more detail now. So we have three basic options here that we'll consider: the correlator A platform, the correlator B platform, and the correlator C platform. This is what correlator A looks like. It's based on a single microcontroller. So we have a single processing unit, in this case running a TT scheduler with one task set operational at any particular point in time. We have a predictor mechanism, we have a monitor mechanism, we have information about the mode and state, we've got configuration mechanisms used in the system. So we're storing the task sequence data for our predictor mechanism, we're storing task data that we're also using to run the scheduler and for our monitor mechanism, and we have an internal watchdog timer. So we have no external monitoring components here. We do have an internal watchdog timer, and we do have the internal monitor and predictor mechanism. Let's look at an example of a correlator A platform. Let's start with the safety architecture. This is a 1 out of 1 safety architecture. This means that the system contains only one processing unit, and that processing unit must be operational if the system is to remain safe. We also have a functional architecture. This is also 1 out of 1. There's only one functioning processor. If that processor is not operational, the system can't function. In this case, the 0 at the end here illustrates that this is a design that is based on a SIL0 MCU. That is, it's based on a single microcontroller that is not safety related. You'll find a full explanation for the names used for the patterns at the beginning of Appendix 3. It might be useful to take a look at that. So in this case, what we have is a 1 out of 1 safety architecture, a 1 out of 1 functional architecture, a single microcontroller that is SIL0 in nature. There's no external hardware. There's an internal monitor, an internal predictor. We'd usually expect to perform built-in self-tests with the same mode reset around once a day in this kind of design. To emphasize again, this is not going to be used in a safety-related system, and there are no external monitoring components. Let's look at another example of a correlator A design. This is the same as the previous version that we looked at on the previous slide. There's still no external monitoring. This time, however, we're using a SIL1 microcontroller, and we have a design that may be suitable for use in applications up to SIL1 in nature. This slightly changes the way that we perform the built-in self-test. This is the main change for this application as far as the developer is concerned. So to achieve the required safety integrity level, we would expect to perform same mode resets around every 30 seconds with this kind of design in order to ensure that it was operating correctly. No, this is not a rule, it's simply a starting point, a starting guideline. You may decide in your application that more frequent or less frequent built-in self-tests are required, or you may have an alternative way of implementing these built-in self-tests. There are no hard and fast rules. This is simply a guideline to indicate what you might wish to consider at the beginning of your design discussion. Let's now look at a correlator B design. This is a little different. So now we have an external watchdog controller, the kind that we discussed in video 17. This is now a 1 out of 2 safety architecture. So we have two processing units that are responsible for safety, and as long as one of these is operating correctly, the system can function safely. Notice that it's still a 1 out of 1 functional architecture because only MCU-A is performing useful functions in our design. The external watchdog controller is simply a power-off device in most cases. It has no more complicated functionality than that, so it serves a safety function, but it doesn't otherwise contribute to the operation of the system. In this case again, we're assuming that we're using a SIL1 microcontroller, we've got a suitable external watchdog controller, internal monitor and predictor, and we're assuming that we would probably perform same mode resets every 10 minutes or so. We assume that it's likely to be possible to perform the built-in self-tests at a less frequent rate in this design because we have the external watchdog controller. But again, the precise rate at which you perform such checks and resets will depend on the application requirements. This is then a correlator B2 design. This is essentially the same as the last one we looked at, but now we're assuming that we're using a SIL2 microcontroller, which allows us to achieve a SIL2 rating for the platform with this software architecture. The other aspects of the design remain essentially the same in this case. Now let's say a little about ASO decomposition again. Let's assume we're developing an automotive system, some kind of electronic control unit for use in a passenger vehicle perhaps. We'll assume that this design has been identified following the processes defined in ISO 26262 as having at least one functional safety requirement. We'll call it functional safety requirement X, FSRX, at automotive safety integrity level D, ASO D, and that the task of meeting this SFR has been allocated to our ECU. We will further assume that through a process of ASO decomposition, again as defined in ISO 26262, we have decomposed FSRX into two new FSRs, FSRX1 and FSRX2, each of which is at ASO BD. So this is the decomposition that we have carried out in this design. We've started with an ASO D functional safety requirement, and we've decomposed this into two ASO B brackets D functional safety requirements. And we're assuming that it will be less expensive and more straightforward to implement the software for these two sets of independent ASO B requirements. So in general, the cost of meeting these two FSRs at ASO B is expected to be significantly lower than meeting the original FSR at ASO D. However, to justify such an ASO decomposition, the two new functional safety requirements must be implemented independently, and it must be possible for the development team to demonstrate clearly and unambiguously that the two implementations are independent. So we need two independent implementations of these decomposed FSRs. One way of providing an independent implementation is to begin by allocating these two FSRs to different microcontrollers, but this is likely to be too expensive for many automotive designs. An alternative is to provide implementations that meet both FSRs by means of the same microcontroller. We can do this if and only if we are able to ensure that the two implementations will be able to operate independently. The decompositor platform, in this case decompositor B, is used to support ASO decomposition usually. It can be used to support SIL decomposition, but ASO decomposition is a more common use for this platform. So here I'm illustrating a situation where we have a single microcontroller, a single scheduler, which is usually a TTC scheduler, and we have two task sets running in an interleaved manner. Task set A and task set B. So we essentially run both of these task sets interleaved on the same scheduler. And we would design these task sets using as diverse tasks using the techniques that we discussed earlier in this course. So we have two task sets running in an interleaved manner on a single scheduler on a single microcontroller, and we will have, in this case, because it's a B platform, we'll have an external watchdog controller assessing and checking that the system is operating correctly. As an example, this is what a decompositor B3 design might look like. So this is a safety architecture, which is again 1 out of 2. So there's one microcontroller and an external watchdog device, an external watchdog controller device. So if we have a 1 out of 2 safety architecture, we only have one microcontroller, so it's a 1 out of 1 functional architecture. The maximum SIL rating for the platform is expected to be ASO-D, because we're using a single ASO-D microcontroller. The external hardware that we need is a suitable external watchdog controller, and we have the monitor and predictor components implemented internally. Again, simply by way of guidance, we might expect to perform built-in self-tests with the same mode reset around every 10 minutes on this platform. So the two main standards that we've compared during this course, ISO 26262 and IEC 61508. There is a lot in common between these two standards, but there are also some important differences. At the start of the introduction to each part of ISO 26262, we find the following. ISO 26262 is the adaptation of IEC 61508 to comply with needs specific to the application sector of electrical and/or electronic systems within road vehicles. Despite these origins, there are some significant differences between the two standards and the way that they are applied. One important difference between these standards relates to the concept of hardware fault tolerance in IEC 61508. Where we have a hardware fault tolerance of 0, this means that we have only a single processing path available. If this fails, our goal must be to ensure that the system can enter a fail-safe state. When we have a hardware fault tolerance of 1, we have a second processing path available. If one processing path fails, we may be able to continue to operate the system for a while, possibly in a limp home mode. HFT is an important consideration in IEC 61508, but it's not explicitly defined in ISO 26262. As an alternative, ISO 26262 considers single point fault metrics and latent point fault metrics. Please see the standard ISO 26262 Part 5 Clause 8 for further details of this. One consequence of the difference between these standards is that developers of IEC 61508 systems are likely to focus on the use of duplicator type designs with a hardware fault tolerance of 1, whereas developers of ISO 26262 systems may be more likely to focus on the use of decompositor type designs based on a single lockstep MCU. So we've already looked at decompositor type designs. Let's begin to consider duplicator type designs. So we talked about ASO decomposition. SIL decomposition also applies and is sometimes used in this area. So according to IEC 61508, we can sometimes decompose functional safety requirements at SIL 3, a single functional safety requirement at SIL 3, into two independent functional safety requirements at SIL 2. Again, we might expect such a decomposition to result in a cost saving without compromising safety. In IEC 61508, we are more likely to implement these two independent functional safety requirements, the result of our decomposition, on two independent microcontrollers. So this is a generic example of such a 1 out of 2 design, a traditional 1 out of 2 design. So we have two microcontrollers doing some processing, and then we have a third decision unit that decides, based on the inputs from these two microcontrollers, what our system should do. This is just a more general example of a 1 out of 2 architecture. So we have a 1 out of 2 framework here. One subset of this 1 out of 2 design option is a 1 out of 2 fail-silent or fail-safe option. And a subset of that is a 1 out of 2p option. So a 1 out of 2 power option is one way in which we can implement a 1 out of 2 architecture. So this might look something like this. This is an example of a 1 out of 2p design. Here, each microcontroller controls a power switch. Unless both MCUs agree, no power is supplied. This is assumed to be a safe state. We can achieve SIL3 using two SIL2 MCUs and an appropriate software architecture in this way. So this form of 1 out of 2 design doesn't require a third microcontroller to make a decision. Instead, the decision is effectively made through this form of AND gate. Only if both microcontrollers are happy will power be supplied, or will an enable command be made to a piece of equipment. We can implement this kind of 1 out of 2 design effectively using a duplicator A platform. So this is one example of a duplicator A platform. The individual components here should be familiar to you. So we have monitor mechanisms in each case, we have predictor mechanisms in each case, we have the system configured in much the way that we would expect from our previous discussions. What we also do though is we have a cross predictor arrangement. So the predictor in control unit 1 on this slide is checking the task sequence for the second microcontroller. So this task sequence represents the expected task sequence for this microcontroller. Similarly, this task sequence represents the expected task sequence for this microcontroller. This gives us a greater degree of confidence that we will be able to detect any deviations from the expected task sequence while the system is running. So typically we might link our two microcontrollers together in this kind of design using some form of UART link to support the communications between them. And we've discussed the advantages of using a UART link between two microcontrollers in previous videos. Here's another example of a duplicator design, again potentially in an IEC 61508 application. So here, this is a duplicator B design. So in this case, we have an external watchdog controller, and in this design, the external watchdog controller only operates if a pulse chain is generated from both of the microcontrollers that it is working with. So we now have a case where we require MCU A, MCU B both to be happy, and the external watchdog controller to be happy before power is supplied to what we assume is our robot control system. So this is an example of a duplicator A22 design. Again, if you have a look at Appendix 3 in the ERES2 book, you'll see exactly how the naming convention goes together. But this is now a 1 out of 2 safety architecture. We have two microcontrollers, a 1 out of 2 safety architecture. We have a 1 out of 2 functional architecture, because in the event of one of the microcontrollers failing, it may be possible to implement some form of basic, possibly short-term limp home behavior while a single microcontroller is operational. We may be able to obtain a SIL3 rating for this platform through the use of two SIL2 qualified microcontrollers working together. We don't require any other external hardware apart from these two microcontrollers. We will implement an internal monitor on each microcontroller, and we'll use a cross predictor to provide cross checks between the different microcontrollers. We don't need to do very frequent built-in self-tests typically with this kind of design, because we have extensive cross-checking going on anyway. So typically our full set of built-in self-tests would be carried out every hour plus in this kind of design. But again, this is only a guideline. You need to consider the diagnostic test interval for any particular design carefully. That brings us to the end of this video. Please read Chapter 21, Chapter 22 and Appendix 5 in the ERES2 book before you continue with the course. Thank you for watching.